In this series of videos, we will be using the derivative to find the maximum and minimum values of a function.
Alright, well hi everybody. So now we're going to take a look at solving maximization problems, or minimization problems actually. Probably extreme values problems would be a better way to state that. And what we're going to do here is we're going to find places where functions reach their maximum value, reach their minimum value. Okay, and we'll see if we can glean some important information out of that. Okay, now you're going to recognize a lot of these problems from courses that you've done earlier than this, but you're going to see us approach these in a new way, and I'm hoping that you'll see it in a much more efficient way. Okay, now there's not a lot by way of theory to introduce this. Really what we want to do is just kind of jump right in and have you have a look at what this looks like. So let's take a look at a problem here. The lifeguard at a public beach has 400 meters of rope available to lay out a rectangular swimming area using the straight shoreline as one of the sides of the rectangle. Whoops. One of the sides of the rectangle. What dimensions should she use to maximize the area? Okay, so we've got the shore right here. Okay, and so she's going to lay out the rope in a rectangular shape here, where let's say the width is x, the length here is y. Okay, and what we want to do is figure out what those dimensions are, x and y, that maximize this area here. Now you probably recognize this from the quadratics chapter that you would have looked at in a previous course here, and you probably would have solved this by setting up a quadratic function and then completing the square to find the vertex, the maximum. Okay, well we're going to do this a little bit differently here. We know that two x's and that y are going to equal 400. Okay, because we had 400 meters of fencing total. So our fencing is going to start here on the shore, come out, go across, come back in. We also know that we are trying to maximize the area. Okay, and the area here is going to be x multiplied by y. Now, this is the function that we really want to create here. Anytime I'm asking you to maximize or minimize some value, that's the variable that I want an expression for, that I want an equation for. So what I'm going to do here is I've got two variables here, and I really don't want that. Okay, I should say three variables. What I really want is just a relationship between two variables. I want area as some function, and I don't really care if it's x or y, to be honest with you. It makes really no difference in how I'm going to approach this. But let's go over here, and just like we would have done with quadratics here, let's solve for y. So y is going to equal negative 2x plus 400. And when I know that that expression exists, I can I can substitute that into my expression for area. So area is going to equal x multiplied by negative 2x plus 400. And when I multiply that through, I'll get negative 2x squared plus 400x. And so there's my expression for area. Now, at this point, my approach to this problem is no different than it would have been when I was back studying quadratics. In fact, I'm doing the exact same thing. No difference at all. It's at this point here that things are going to change. Because in the quadratics chapter, then what I would have done is completed the square on this to find the vertex. Now, I am, by the way, familiar with this shape here, and it's worth commenting that this is a parabola that opens down. So I do know that it is going to have a maximum. Okay? But let's just take a quick look at this. Another way of dealing with this problem is not by completing the square, but by taking the derivative. So if I take the derivative dA by dx, okay, if I take the derivative of this, I will get negative 4x plus 400. So there's the expression. Remember, that's the expression for the slope of the tangent at any point along the curve. Now, I know that this is a parabola that opens down. I also know that the slope is going to be 0 at that vertex. So what I'm going to do here is I'm going to replace, or maybe I'll even do it over here. I'm going to set that derivative equal to 0. I'll bring that negative 4x over, so 400 is equal to 4x. And when I divide, I'll get that x is equal to 100. Okay, so this is telling me that the width here should be 100. So the width is 100 meters, and the length is, well, if this is 100 and this is 100, that would mean my length would have to be 200, because remember, there's 400 meters of fencing total. So my length is 200 meters. Now at this point, somebody might be out there crying foul, saying, well, wait a minute. Granted, I know that this parabola opens down, but I haven't really demonstrated that using any kind of a calculus tool here, and you're absolutely right. So what I want to do here is, granted, I took the derivative, set it equal to 0, and I found a critical number, okay? I found the critical number of the function. But I do want to use calculus to verify that this is in fact a maximum. So actually what I want to do here is I'm going to take a quick look at the number line. And I encourage you as often as you can to use knowledge you've gleaned from other courses. Don't take calculus all as its own separate little bit of knowledge here that you're going to compartmentalize and kind of keep separate from everything else here. You want to go back and enhance what you understand of calculus by comparing it to things that you've learned in previous classes. So, for example, I want to take a quick look at my derivative here. Just take a look at that function. That is a linear function with a negative slope and a positive y-intercept. So if I was to just take a look at how that intersects with the x-axis, sorry, if this is my x-axis, if you will, and I'm graphing my y primed or my a primed instead of the y value, I'm going to get a graph that goes like this. And I know that it's going to intersect the x-axis at 100. Okay, so I'm going to just give myself a little sketch of the derivative. This is a sketch of the derivative. I can see that if I pick a value to the left of 100, that my derivative is positive. I can see that if I pick a value to the right of 100, my derivative is negative. Okay, and so I think back what that means. That means my function, okay, my a function, a of x, is increasing on the interval. Now, I really can't say negative infinity to 100 because it doesn't exist. I mean, there is no way I can have a width here that's less than 0. Okay, I mean, it could be 0. I suppose we could just lay the rope along the shore. It'd be pretty useless, but I suppose you could argue that 0 would be our minimum there. Seems kind of ridiculous, but up to 100 for sure. And then a of x is decreasing, okay, on the interval. Now let's think about this. 100 out to what? Well, again, I really can't go out to infinity here. I mean, what's the maximum that could possibly be? Well, really what I could do here is I could be taking that rope and just running it straight out and right back out back to shore there. So I come out 200, go back 200. So that is basically as good as it's going to get. Now, again, that's kind of a ridiculous answer, but that's okay. The whole purpose of this little bit right here is to demonstrate, therefore, when x is equal to 100, because I increase to 100 and then decrease after 100, when x is equal to 100, we have a maximum. Okay. Now in this particular case, I knew it was going to be a maximum before I did that. Because I knew this. I knew what that graph was going to look like. I already had an understanding of what that parabola was supposed to look like, so I didn't really need to do that. But I introduced this little bit of reference to the calculus of this scenario here about how we understand increasing and decreasing intervals here, merely to show that this work here corresponds to this work right here. And in a little while here, this is probably going to be a much easier way to determine whether we're looking at a maximum or a minimum than this right here, because some of those functions won't be as intuitively obvious as this one was. Okay, let's take a look at another example. Okay, let's take a look at this example right here. It says, a box with a square base and an open top must have a volume of 4,000 centimeters cubed. find the dimensions that minimize the amount of material being used. Okay, so now if you compare this to the previous question here, now we're looking for a minimum value. And you might think of an application of something like this. If you're in manufacturing, I mean, you typically want to minimize the amount of material you use when you're packaging something. Okay, you might not have much control over the volume of the object you're packaging, but you might have some control over that surface area. Anyway, it always helps to have a look at this scenario here. So we've got this open top box, and we know that it's got a square base. So let's just say that the base is x by x, and then I have no idea how tall it is here, so let's just call that y. What I do know is that my volume here, okay, which would be x squared y, okay, length times width times height, that is supposed to equal 4,000. So I do know that relationship right there. Okay, good. But what I want to do here is I want to minimize the surface area. So I'm going to come up with an equation for the area. Now, in this particular instance here, we're talking about an open top box. So there's no lid. There is a bottom, though. Just so that you're aware, we didn't have to make it an open top box. We could very easily have put a top on it. It really wouldn't have changed much. But this is kind of a standard sort of question here. So my surface area here is going to be, first of all, x squared. That is going to be the base. And then each one of these sides is going to be exactly the same, and there are 4 of them. So 4xy. Okay. Now, I am going to take the derivative of my area function. Okay. This is the variable that I want to find the minimum of. This is the variable that I'm going to take the derivative of. Now, my problem is that I've got this expression in terms of 2 different variables. Now, I really could jump right in and take the derivative and do it implicitly, treating these as 2 different functions here, but I may be making that out to be harder than it needs to be, because I've got a relationship here that I can use to substitute in to get rid of one of these variables here. Now, you might look at this and think, I'm going to be lazy. I'm going to solve for x squared and make that x squared equals 4,000 over y. And actually, I applaud that kind of thinking. You're wrong, because it's not going to make it that much easier. But I like that sort of thinking where you might get rid of the x squared here. The reason why that's not the best way to go here is because you're still stuck with an x right there. And if you isolated the x squared, you'd have to take the square root to get rid of that x right there, and you're making it harder than it needs to be. In this case here, it's probably the smartest thing to do here is to isolate the y. And granted, you're putting an x squared there, but the y only shows up once here, so I only have to do that one substitution. So I'm going to get x squared plus 4x, and I get 4,000 over x squared. I'll do a little bit of simplification here. I get x squared plus, well, okay, I've got an x divided by an x squared there. So I'm going to get an x in the denominator. Now that's true. That is true so long as x does not equal 0. But I think we can all agree that that's a pretty safe bet that it's not 0, because if x is 0, then all you've got is this straight line y there, and there's no volume. So that really doesn't make sense anyway. But that's what the algebra is telling me. And so I'm stuck with this right here, x squared plus 16,000 over x. Okay, good. Now I will take the derivative. Okay, well, the derivative of x squared, that's pretty straightforward, 2x. Now, remember, this expression right here can be rewritten as 16,000 x to the negative 1. In fact, that's probably the easiest way to take the derivative when it's written like this, because now, bring down the exponent, negative 16,000 x to the negative 2. Okay, now, I don't have a clear idea of what this graph looks like. Okay, I don't. And the reason I don't is because although I've got this quadratic term right here, I've got this rational term. So it's not immediately obvious to me what this graph is supposed to look like. Okay, so, but I do know that when I take the derivative, okay, all I really got to do to figure out if I've got a minimum or a maximum there is to set this equal to 0. Because I'm looking for critical numbers. Now, I am going to get a critical number here, and it's important to identify this. It looks like I'm getting a critical number here at 0, okay, because the function is undefined there. But remember, I did that little cancel out there. X can't be equal to 0, and even besides that, it's an asymptote right here. Like no matter how I cut this, X can't equal 0. So that's okay. So now I'm going to bring that 16,000 x over x squared over. That'll be 2x is equal to 16,000 over x squared. I will multiply that up to get 2x cubed is equal to 16,000. Divide by 2. X cubed is equal to 8,000. And then actually that number is incredibly convenient to work with because the cube root of 8,000 is going to be a nice 20. Wonderful. Wonderful. Except for one little thing, and that little thing is, I don't know that that's actually a minimum. Okay, now I haven't figured out the y coordinate yet, and I will in a bit. But unlike the previous question, I don't know prior to this point here, is this actually a minimum? So let's just take a quick look here. Okay, it doesn't make sense. It doesn't make sense to take a look at anything less than 0 here. So here's my 20, and there is very likely a natural maximum to this right now, but really all I need to do is investigate what's going on either side of 20. Okay, so let's take a quick look at this. If you plug in, for example, let's plug in 10. Okay, let's just plug in 10 into this. If you plug 10 into your derivative, 2 times 10 is 20. Okay, and then I'm going to subtract 16,000 over 10 squared. Well, that's going to get me 20 minus, bear in mind that's going to get rid of those 2 zeros there, because 10 squared will be 100. That's larger, so this is actually going to be negative. Okay, that's going to be negative. If you plug in a number bigger than 20, let's say 30, well, 2 times 30, okay, is going to be 60, and then we're going to subtract from that 16,000 divided by 30 squared. And actually, that's going to get you a positive. And on my calculator here, I've got a 42.2. That's going to be positive right there. So I know that my function, my area, is decreasing. Okay, is decreasing. Now that's going to decrease here from 0, and I'm including 0, even though that's a ridiculous answer. Oh, sorry, I shouldn't even include 0. My mistake. I shouldn't even include 0 here. Okay, from 0, because that's an asymptote, from 0 up to 20. And then A is increasing from, whoops, sorry, I do want to include this, from 20 up to, now, hard to say what my maximum would be there. Okay, I suspect it's going to be the, what we got here, like the square root of 4,000, but there's going to be a maximum there. Now, just because right off the top of my head, I'm not motivated to find that because it's going to drop out here, I'll just throw in an infinity there. Just a little cheat, because really all I'm interested in right now is the behavior around the 20. Although there is a natural maximum to what that would be. So I do know I can see this, therefore, okay, when x is equal to 20, I have, or I think I said maximum a couple seconds ago, I have a minimum. Okay, I definitely have a minimum here. So the width, okay, the length and width are 20 centimeters. Okay, now that gives us the depth. Now remember, if you're wondering, well, how on earth do I figure that out? Well, that's coming from up here. So all we're going to do here is divide 4,000, okay, by, what is it, 20 squared, which is going to be 400. And so what we'll end up getting here is that the y is equal to 10. So a depth of 10 centimeters. X is equal to 20 centimeters. Y is equal to 10 centimeters. And there's our answer. All right, now in this problem, we read that we're being asked to find the points in the parabola y equals 6 minus x squared that are closest to the point 0, 3. Okay, so 6 minus x squared, if we just get a look at that, 6 minus x squared is going to be a parabola that opens down, okay, from the point 6. And then we're looking for the shortest distance to the point 0, 3. So we're looking for the shortest distance to that point. So where is this parabola the closest to this point right here? Now I'm going to do this in two different ways. And then you can kind of decide which method makes the most sense to you. It doesn't really matter. One method I think is a little longer, but it probably makes more sense. The other method is a fair bit shorter, but I think it's a little bit less clear what's going on here. So anyway, here's method 1 here. So what we're going to do is we're going to choose a kind of a random point on that parabola here. We're going to give it the point x comma y. Except that that's not actually very useful to me, and if I'm just going to use the variables x and y, that doesn't actually guarantee that that point is on the parabola. Okay? Because the point x comma y could be anywhere on the grid. I mean, x and y are completely random, so how do I guarantee that that actually is on the parabola? Well, what I do is instead of using the y, I use the function. So now my point is x comma 6 minus x squared. And by doing that, I guarantee that this random point that I'm choosing here is actually one of the points on that parabola. Okay? So now, we're going to find the distance between this point right here, which we know is fixed at 0, 3, and this point right there. Okay, we'll call that D. So our D here, and we've got the distance formula, is going to be the square root of x minus x, okay, so x1 minus x2, so x minus 0 squared plus y minus y. So 6 minus x squared minus 3 squared. So my distance is going to be x squared plus, okay, well this is going to be 6 minus 3, so this will end up being 3 minus x squared squared. I can simplify that a little bit further, okay. I can make this, for example, I can make that 9 minus 6x squared plus x to the 4th. And then I will write this in a form that's a little bit more useful to me. I'll write this as x to the 4th minus 5x squared plus 9. Okay, now before I jump into this and minimize the distance here, I am pretty lazy. So what I'm going to do first here is I'm going to square both sides. I'm going to get d squared is equal to x to the 4th minus 5x squared plus 9. Now the reason I do that is just because I'm a little bit lazy. And I don't really want to take the square root of that, the derivative of that square root there. So I'm going to square both sides, and now when I take the derivative, I'm going to take the derivative, and again, I'm taking the derivative of my distance formula because I want to minimize the distance. Okay, so I get an expression for distance. That's what I take the derivative of. Doesn't really matter that I got to do it a little bit implicitly here. This will be 2d, and I know this is going to seem a little bit weird here, but dd by dt. dt by dx here. Okay, let's just change that to a dx. Do so many related rate problems, sometimes I forget this is not a related rate, we're maximizing and minimizing this. And on the right hand side, this will become 4x cubed minus 10x, and then the derivative of 9 is just going to be 0 there. Okay, so now when I solve for this derivative here, I got dd by dx is going to equal 4x cubed minus 10x over 2d. Now, I've got two variables here, but actually that's not going to end up being a problem because remember, what I'm trying to do here is minimize the distance there. I'm going to find the smallest value. So what I want to do here is set that derivative equal to 0. And then when I multiply through by the 2d, it basically goes away here. So I go right back to 4x cubed minus 10x is equal to 0. And we would have gotten to the same spot here even if I had left the square root in. And so now to solve this one right here, I'm going to factor out, what do we got here, a 2x. And so that is going to leave me with 2x squared minus 5, which is equal to 0. And now to solve that, either x is equal to 0 or x squared is equal to 5 halves, in which case x is equal to the positive or the negative square root of 5 halves. Now, some of you may be expected to rationalize that as well. You have to figure out what the expectation is from your teacher, in which case this will be plus or minus root 10 over 2. Okay, and so right there, those will be the x coordinates. Okay, I've got 3 x coordinates right now then. So that doesn't make it clear to me right off the bat here, well, which of these are going to give me the minimum? Okay, well, let's take a quick look at this. Let's take a look at our number line here. And we'll throw these on there. So we're going to have negative root 10 over 2. We got 0. And then we've got positive root 10 over 2. And what I'm interested in right here is the behavior of the derivative. So let's go up to this derivative right here. Okay, now bearing in mind that my distance is always going to be positive. Okay, my distance, if you go back up to the beginning here, my distance is always equal to the positive square root. So really what's happening here is this 2d in the denominator is not going to affect the sign of the derivative. So really I can just spend my time looking at that 4x cubed minus 10x. That's a cubic expression. Okay, it's a positive cubic expression, meaning that if I think about what its shape is going to look like, it's going to come up through here, back down, and go up. It's going to look like that. Okay, that's what the 2d in the denominator won't affect this. Okay, meaning that the first derivative is going to be negative in this interval, positive here, negative here, positive here. So because the first derivative is positive and negative in those intervals, I know that my function is going to be decreasing, okay, on the interval negative infinity to negative root 10 over 2, and then union 0 to positive root 10 over 2. And then it's going to be increasing on the interval negative root 10 over 2 to 0, and then union positive root 10 over 2 out to infinity. And what that tells me, because it's decreasing to here and then increasing afterwards, this right here represents a min, this is going to be a max, and this here is going to be a min. So what are the points on the parabola that are closest? Okay, they're going to be closest, okay, when x is equal to either positive or negative root 10 over 2. Now, let's plug that in because we're supposed to get the point here. So if x is equal to negative root 10 over 2, now how do I get my y coordinate? Well, I go way back up to my function. Negative root 10 over 2, okay, is going to end up being, what's going to end up being 10 over 4, okay? And so now if we take and subtract that from 6, now 10 over 4, okay, is going to be, so it's going to end up being 3.5, so that means this is actually going to have the coordinates 7 over 2. And then if you plug in positive root 10 over 2, because of the square in the parabola, it won't matter here. The result is going to be the same. It'll be positive 7 over 2. So what's happening here is there are points right here, okay, probably right there and right there, that are the closest to that point 0, 0, 3. So what happens here is as we take this random point and slide it along, well, let's maybe start over here. From negative infinity, we slide it along the parabola. We get closer and closer and closer to this point until we hit right here. But then for a very brief little interval, we move away. And so that's why this becomes this little maximum. And then once we get past the maximum, we move back towards it. We hit this minimum distance. And then as we slide the point along here, we continue to move away from that point. And so that's what's going on. Now, that's one method of handling this problem. I'm going to show you another one. Okay, now we're going to take another look at this question. This is going to be our method 2. So we're still looking at the same parabola here that opens down. And again, we've got that point at 0, 0, 3. And again, we're going to choose a random point on there, but we know now that this has got to have the coordinates x comma 6 minus x squared. But this time we're going to approach this a little bit differently. Okay? And now in the previous question, when we did this question before, we found the distance from here to that point on the parabola, and then we found an expression for it in terms of x, and then we took the derivative to minimize that. Now we're still going to minimize this distance, but we're going to approach it in a slightly different style here. What we're going to do is we're going to apply a property of the geometry here to make this answer pop out for us. So when we connect that point, 0, 3, to a point on the parabola, okay, and we compare that to the tangent line here, we're going to get some angle here, theta. Now, as this angle, as this point here, as you slide that point down along the parabola, out along the infinite length of this parabola, that angle is going to get smaller and smaller and smaller. As you move it back up, it's going to get larger and larger and larger until you hit a point somewhere here where that tangent line is going to be perpendicular to that line segment connecting it. That's the instant that we're interested in, because that is going to be the minimum distance along here. Okay? Anytime you slide this over a little bit, okay, if you move that over, that angle becomes less than 90. That side is going to be longer than it is when it's right there. Okay, now I'm not going to prove that to you necessarily. I think for a lot of us that's kind of an intuitive thing. You can prove it, but we're not going to do that right now. We're just going to jump in and utilize that. Okay, so what I need to do then is I need to find the slope of the tangent and the slope of that line segment connecting that point of tangent to 0, 3. Well, the slope of the tangent is easy. This is a calculus class. We've got the y equals 6 minus x squared. So the slope of the tangent is going to be y primed, or negative 2x. That's the slope of this line. The slope of the line segment joining 0, 3 to that point of tangency, well, I've got 2 points there. Remember, I've got this general point and I've got this one right here. Sometimes for calculus students, this is the less obvious of the two, because you get so used to taking derivatives you forget the definition of the slope. Okay, so now it'll be y2 minus y1 over x2 minus x1. And so we're going to get here 3 minus x squared over x. Now, these two are not equal to each other. I mean, they're clearly not equal to each other. They're perpendicular to each other. But it's the fact that they're perpendicular to each other that we're going to now utilize. Because when two line segments are perpendicular to each other, the product of their slopes, okay, the product of their slopes is going to be negative 1. And now once we've got this equation set up, now we've got something we can solve here. Now, I know right away that we would look at this and you might think to cancel out the x's there. And we totally could do that. But I don't want to right now. Okay? I don't want to do that right now. I want to leave that in. Okay? And you'll see why in just a moment here. So I'm going to multiply through by that numerator. We're going to get negative 6x plus 2x cubed over x is equal to negative 1. Now, the reason why I don't want to necessarily cancel those out is because if I cancel out the x's, I'm actually going to lose a solution here in a little bit. Now, granted, if x is equal to 0, okay, if x is equal to 0, this is undefined. And that makes total sense, because if x is equal to 0, then this point has moved up to the vertex, and the slope of that line segment joining this point to that vertex is undefined. And that makes total sense here. However, I do want that 0 to pop out. Even though I know that it's going to cause this to be undefined, I'm okay with that. I understand what that means. That's why I didn't cancel it. If I had canceled that out, I would have lost that solution. I'm instead going to multiply both sides by that x, and I'm going to get negative 6x plus 2x cubed is equal to x. Now I'm going to bring that over, and I will get negative, sorry, that was negative x over there, because I have to add that when I bring it over here. And I'll get negative 5x plus 2x cubed, whoops, is equal to 0. Now I can factor out the x, and then I'll rearrange it a little bit to get 2x squared minus 5 is equal to 0. X is equal to 0, or x is equal to plus or minus 5 over 2 square root. Okay, square rooted there. And so we're right back to where we were with that other equation. Now, when I want to check for the intervals of positive or negative, bear in mind that when I do that, I'm using an expression, I'm using the derivative set equal to 0. So what I would do here is I would look for my expression where it's set equal to 0. The moment that I solve that, okay, this expression right here is the one that I want to check to see whether it's positive or negative, right? I mean, if it's equal to 0, I'm looking for critical numbers. If this is positive, then the function's increasing. If it's negative, then it's decreasing. Okay? So from here, we would explore this just the way we did in method 1 here. So this method here is a little quicker, okay? But it requires you to make a connection here between the slope of the tangent and the slope of that line segment connecting that point to the point of tangency. Knowing something about the perpendicular slopes, which you should know, by the way. But it's not quite as obvious as just finding an expression for the distance, taking the derivative and setting that equal to 0. So either one. Okay, now this next question, this is a really common style of question, what we're about to do here. Determine the dimensions of the cylinder with a maximum volume that can be inscribed in a sphere of radius 10 centimeters. You will see a lot of these sorts of questions in a calculus class where we take an object and we constrain it with another object, but we look at how we can maximize its volume or its dimensions or its area or whatever, given that it's restrained by another object here. So what we've got here is we've got this sphere, and it's got a radius of 10, and we're going to take, a cylinder, draw it in that sphere, and we want to figure out what's the biggest cylinder, what's the volume of the biggest cylinder, or actually in this case, what are the dimensions of the cylinder that has the largest volume. So now when we talk about the dimensions of a cylinder, what we're talking about here is its radius. Okay, now it comes around like this. Its radius and its height. Okay, those are the two things that we're looking for. Now, we know that the radius of the sphere is 10. Okay, and so we might be tempted to draw this little right angle triangle here because it's going to give us a relationship between these. In fact, specifically, what we're going to see here, okay, is that the radius of the sphere is 10. This would be half the height of the cylinder, and here's my radius. Which means the relationship between these is going to be h over 2 squared plus r squared is equal to 100. And then just to clean this up a little bit, that's going to be h squared over 4 plus r squared is equal to 100. Good. So that's the relationship between h and r that I find because this cylinder is being inscribed in a sphere. Now, if I want the maximum volume, then I need an expression for volume. Okay, well, I know that the volume of a sphere is going to be pi r squared height. Okay, now I've got three variables here, v, r, and h. I would prefer it if there was only two. I really want v there because I'm looking for the maximum volume, so I need to take the derivative of the volume expression. So it's really r squared or h, or r or h I should say, that I want to get rid of. Now I would be very tempted to use this expression right here to get rid of r squared. Like, I'm very fortunate that there's an r squared here in this relationship and there's an r squared right here. So I know r squared is going to equal 100 minus h squared over 4. Well, I love that. So now I'm going to come to my volume expression, and that's going to be pi 100 minus h squared over 4 multiplied by h. And when I distribute those pieces through, I'm going to get 100 pi h minus pi h cubed over 4. Now I love that because now I've got an expression for volume, and it's just in terms of h. Okay? And I owe that to the fact that it's being inscribed in this sphere, so that I was able to find a relationship, a nice clean relationship between the radius and the height of that sphere. Okay, so now we are going to take the derivative of that volume with respect to the height, because that's the only variable I've left myself here. So that will be 100 pi minus 3 pi h squared over 4. Okay. I want to maximize this. I'm looking for the critical numbers, so I'm going to set my derivative equal to 0, and I'm going to solve for the unknown there, so for the variable. So I'm going to bring that over. So this will be 100 pi is equal to 3 pi h squared over 4. Pi's are going to cancel. I'm going to multiply by 4, so I'm going to get 400 divided by 3 over 3 is equal to h squared. And then I'm going to take the square root. Now when I do that, that's the positive or negative square root of 400 over 3. Now I know someone's going to say, wait a minute, time out. Plus or minus, what? We're talking about a shape here. And I know. But from here to here, the correct algebraic step is to state, okay, that it's plus or minus the square root of 400 over 3. Now, I know that the negative here doesn't really make any sense, so we're just going to cancel that out here. But I'm also going to distribute that root through, so this is going to end up being 20 over the square root of 3 is equal to h, or 20 root 3 over 3, okay, centimeters. Okay, bear in mind this is all in centimeters here. If you're being forced to rationalize that, and some teachers expect the students to rationalize. Now, there are a growing number that don't expect that to happen anymore, in which case the 20 over the root 3 would be fine. Great. Except I still don't know what r is. Okay, I know what h is, but I don't know what r is. Now, I do have, though, an expression for r, or at least r squared. R squared is 100 minus h squared over 4. So r squared, whoops, can't see that. R squared is equal to 100 minus, now h squared over 4. Now take a look at this. Oh my goodness, there's my h squared. There's my h squared. H squared is 400 over 3. So that was h squared, 400 over 3, divided by 4. So that is going to be, well, 400 divided by 4, that is going to give me 100 minus 100 over 3, which is going to give me r squared is, well, if I subtract a third of 100 from 100, I'm going to end up with 2/3 of 100, or 200 over 3. That's equal to r squared. And so r is equal to positive or negative the square root of 200 over 3. Okay, but I know that I can simplify that. I also know that I'm only going to take the positive here, so that is going to be positive 10 root 2 over 3, which, if you're being expected to rationalize it, will become 10 root 6 over 3, and this will be centimeters as well. So there's my height, okay, 20 root 3 over 3, and there's my radius, 10, and sorry, you can't see that really clearly, 10 root 6 over 3.